Okay, so I think you have heard or or from reading papers that uh, the traffic in data centers has been growing very rapidly in recent years. So the data centers, uh, are asking for high bandwidth uh, with the high density optical interconnects. So to meet the bandwidth demand, the new fibers have been proposed, such as multi-core fiber, as you just heard the second speaker, or the multi-mode fiber or few-mode fiber. But however, for these new fibers, they have new challenges. For example, we need to have a low cost of fiber manufacturing. Otherwise, the cost would be too high. Also, the fan-in, fan-out or mode max DMAX devices are very important. We need to have reliable, low-cost devices to be used with these fibers, and also for installation, splicing and connectorization are also very important issues. So on the other hand, we can reduce the fiber diameter, to increase the fiber density. For reduced diameter fiber, however, there are also challenges. The two key challenges, one is microbanding performance, the other one is mechanical reliability. So the conventional optical fiber is about 250 micron diameter. If we use this as a baseline, if we reduce the coating diameter to, for example, to 175, so we can increase the fiber density by a factor of 2. If we reduce further, to 145, we can increase by a factor of 3. Of course, if we make a 125 micron coating fiber, we can increase the density by a factor of 4. So currently, the 200 micron, or also people, they launched the 190 micron diameter fiber. Now they're commercially available. Now the question is, can we reduce the coating diameter further? For example, to 165 or below. This is the focus of our paper, in this work. Yeah. So basically, there are two approaches, for reducing fiber diameter. One is you reduce both the cladding diameter and the coating diameter. For example, reduce the cladding diameter to 80 micron. The other approach is keep the cladding diameter to the standard size 125 micron, only reduce the coating diameter. So for the reduced clad diameter fiber, or RCF, one advantage is it has better bending reliability because the glass is thinner. However, the micro bending sensitivity is increased due to a smaller glass diameter, and also for reduce the cladding diameter. You need new connectivity solutions because the current ecosystems is for 125 micron cladding diameter. For the second approach, we keep the colliding diameter the same, only reduce the coating diameter. So the nice thing about this approach is it's compatible with the standard equipment and the installation procedure. And, however, the microbending sensitivity and the mechanical reliability could be a challenge. Could be the new challenges because the coating is thinner. Let's look at microbending first. So we divide microbending into two categories. One is we call the intrinsic microbending. This is basically due to the thermal buckling. When you make fiber, you have the glass and the coating. They have different thermal expansion coefficients. So if the stress is too high on the glass, so the fiber can be buckled. This is not due to the external forces, just due to the fiber structure itself. So we call this intrinsic microbending. The other type is extrinsic microbending. Is when you have external perturbations, you apply pressure or force, so the fiber can be deformed, causing the microbending issue. So for both type of microbending, the glass diameter, coating material and thickness, and the profile design, they all can affect the microbending, both type of microbending performance. So let's look at the intrinsic microbending. So for intrinsic microbending, we define the buckling strain. It's the difference between the strain applied to the fiber minus the strain that glass can tolerate. If this buckling strain is large enough, then the fiber will buckle. So when the fiber buckle, we can use the bending diameter or bending radius to describe the buckling effect. We can calculate the bending radius using this formula. Basically it depends on the glass, radius and the Young's modulus of the glass. So on the right, the plot shows the model, the intrinsic microbending sensitivity. So what you can see that the smaller glass diameter and the thicker coating diameter increases the intrinsic microbending. For example, if we make the 165 micron coating diameter, for the 80 micron glass diameter, the intrinsic microbending sensitivity it's about 9 to 10 times higher than the 125. This is why if you make 80 micron glass diameter, you have put the low index trench to reduce microbending. You cannot use a simple step index, otherwise the microbending loss is too high, right? So of course, you can change the geometry and mechanical properties of fiber coating, and also use a different profile design to improve the intrinsic microbending. For the extrinsic microbending, the microbending loss is basically proportional to this the deformation spectrum. From this spectrum, you can see the most important parameter. One is the glass, diameter and the Young's modulus. The second most important parameter is the primary coating, Young's modulus and the thickness. So the graph on the right, you see the model, the extrinsic microbending sensitivity. So it's clear that the smaller diameter, smaller glass diameter, and the thinner coating increases the extrinsic microbending. So again, we see the advantage of keep the glass diameter, as a standard. So not reduced to 80 micron, because the glass diameter is very important for microbending performance. And also you can again you can improve the Young's modulus and the geometry of the fiber coating material. Also, most important for extrinsic microbending, you reduce the external pressure or force applied to the fiber. For example, you can have a better design of the cable, and also you can use different profile designs, such as trench assisted profile design, to improve the extrinsic microbending performance. This two graphs. One shows the extrinsic microbending as a function for the glass diameter, but for different primary coating. As I mentioned, the primary coating is very important for the microbending performance. We can see from this graph, if the primary coating modulus is reduced, now you can lower the microbending sensitivity. On the other hand, the secondary coating Young's modulus, has almost no effect, on the microbending sensitivity. For the fiber mechanical reliability, there are two aspects. One is the fiber strength. So normally we use a proof test to ensure that the fiber strength distribution has a minimum strength level. For terrestrial applications, the proof test stress level is 700 megapascal or 100 kpsi. This requirement, has to be met by the reduced coating diameter fiber. For another aspect is the puncture resistance. When you have particles, applied to the coating, the particle can damage the coating, and if the particle touch the glass, it can cause damage. So for the puncture resistance, currently there are no industrial standards and test the procedure. So internally, we use we call it a coating indentation test method. We use a sharp object to press against the coating to quantify the damage resistance. So for puncture resistance, you can change the coating material, to improve the puncture resistance. But I think the most important requirement for RCDF is no breaks. When you make when you handle the fiber and make into cable. I think after you make it into cable, you have additional protection protection layers. I think then the coating becomes less important. So we have made reduce the coating diameter fiber. As you can see, the examples show here. We made the coating diameter, from 125 to 170, 75 micron. From these pictures, you can see that the coating, has a very good, geometry, with a very good concentricity and uniformity. For the profile design, we use the 3 type of profiles. So one is the simple step index design, and the second type is dual collide. We have slightly lower inner colliding and raise the outer colliding, and the third type is the trench assisted profile design. This table shows the typical, fiber, the geometry and optical performance. What you can see from this table, for the dual coated fiber, we dual coated fiber with with the coating diameter, the about 140 microns. The attenuation on the shipping rail, almost no penalty, compares to the 250 micron coated fiber. For the single coated fiber, very thin, only a single layer coated fiber, the attenuation is slightly higher, but it's still low enough, for short reach applications. So the attenuation test on shipping rail, they confirmed that the RCDF the fibers have excellent, the intrinsic microbending performance. So for extrinsic microbending performance, we use a wire mesh test. As show in this slide. So basically, we wrap fiber on the a sand paper, and then the apply force. You can calculate the force applied to the fiber. It depends on the winding tension and also the spool radius. So here are the test results for different coating diameters, and also for different profile designs. From the graph on the left, you can see clearly, when you reduce the coating diameter, the microbending sensitivity, increases. So from this data, our analysis show that the micro bending attenuation increase, the scales with this the primary coating thickness and the multi-field diameter. So to reduce the extrinsic microbending, you can use a thicker primary coating or or a lower Young's modulus coating material. And for profile design, you can reduce multi-field diameter or use the low index trench design. As I mentioned earlier, for the extrinsic microbending, the one very important factor is that you minimize the external force applied to the fiber. If you don't have a force applied to the fiber, then you don't have a microbending problem. And to show that, we did a loose coil fiber test. So we use a loose coil diameter of 20.3 centimeter. Then we did temperature cycling because in the cable, microbending, happens most at lower temperature. And so from this temperature cycling on loose coil, you can see different coating diameters. The attenuation change is almost nearly zero, very small. And even the coating diameter 165, the attenuation change is very similar. So these results confirm that if you have no force applied to the fiber, so basically there no microbending problem. So we did also proof tests on the fiber from coating diameter 140, to about 170. For the 160 and 170 micron coating diameter, the break rate increased slightly compared to the standard 242 2 micron. We think we can improve the break rate to a level similar to the standard coating diameter by improve the environmental by control basically the particles in the environment. All the fiber we made in the R&D requirement is not as good as the production environment. On the other hand, for coating diameter, the 140, we see a significantly higher break rate. From this the test result, we think 170, around 160 to 170 coating diameter is feasible. For the puncture resistance, we tested different fiber diameters and different coating diameters. Basically the puncture resistance scales with the secondary coating cross-sectional area. For each given type of coating, basically it's a straight line. When you increase the secondary coating cross-section, but different material, can have a different slope. For example, on this graph, see the blue and the red line compared to the baseline, the normal commercial available coating, the red and blue, has a much better puncture resistance. For example, the blue line, you can have a 165 micron coating diameter with, the puncture resistance, better than the 200 micron coated diameter using the conventional coating material. To show the feasibility of reduce the coating diameter fiber, we did a cable trial. This shows the schematic of the cable structure. It has 8 tubes. Each tube has 24 fibers. 25 for fibers. Then we use the two different, the tube diameters, and then we can change the air fill fraction. Basically changing the pressure or force applied to the fiber during the temperature cycling. In the cable trial, we handle the fiber using the standard tool. We found, we did not have any issues handling the reduced coating diameter fiber. Also, we did not see any fiber breaks during the cable processing, and also the subsequent, the cable testing. Now let me show you the cable result. On the attenuation change, and that shows the minus 40 degree C attenuation change. So from the graph on the top, you can see that the fiber free space has a big impact on the microbending performance. Basically, if you have enough free space, you can reduce the microbending to a certain level. So we use the standard temperature cycling procedure. In the standard, basically they use 0.25 dB as the maximum allowed change at minus 40 degrees C, and so we use 0.15, to in order to have a guard band for our fiber performance. From the graph on the top, you can see that for the 160 and 170 micron coated fiber, so the free space need to be greater than 46, and for the 160, or the 41% for 170 micron, to ensure that attenuation is below the 0.15 dB. Also depends on the design. What I just mentioned is for the dual collide. If you use a trench assisted design for 170 micron coated fiber, the free space can be reduced to about 40%. Yeah. So you may think the increase the free space, basically you reduce the cable density, but if you look at the graph on the lower right, that shows the relative density versus the free space. For a given coating diameter, the free space changes only slightly the relative density, but the coating diameter itself has much bigger impact. Basically you reduce the coating diameter, the fiber much thinner, then you allow a little bit more free space to reduce microbending. For both 160 and 170, the coating diameters, for the free space, the range, we can, it changed slightly, but we still can have a factor improvement, over 2, for the two coating diameters. Okay, so this the last the last the two slides I'm going to show is now we can use thin coated fiber for making connectors using direct ferro insertion without strip the coating. So for this application, we make the coating diameter is 125 micron, the same diameter as the standard glass diameter. But we reduce the glass diameter slightly, to 115. So now because we don't strip the coating, now the fiber with coating is like the standard diameter fiber. So we can insert the fiber with coating, into the connector ferrule to make connectors. So in this way, that we can reduce the damage on the glass significantly, because now the glass has a thin layer of coating, and also we think it can improve the long-term reliability. Because there's no flow on the glass when you insert the fiber into the ferrule. So we made the connectors and tested their performance. Basically the insertion loss and the return loss. We can achieve the performance very similar to the conventional connectors. And also the core to ferrule concentricity, as you can see here, is also similar to normal connectors. Okay, that's come to the end of my talk. So we have shown that the reduced coating diameter is promising for increase the cable density. We have discussed the key design considerations. For RCDF, and we show how to improve the micro bending performance and the mechanical reliability. And we made the RCDF fibers with very good optical and mechanical performance. And our cable trial shows that the RCDF could be cabled with no issues. And finally, we show that 125 micron coated fiber can be used for making connectors without stripping the coating. So we believe the reduced coating diameter fiber, with a diameter less than 175, are promising for high density cable and the connector applications. Thank you very much.